Somewhere in the chemical literature of the 1850s, if you look hard enough, you can find water written at least 3 different ways by 3 different respected chemists, all of whom believed they were correct. Ho. H2O. H2O2. One formula, one of the most fundamental substances on Earth, and the scientific community couldn't agree on how to write it down. That wasn't a typo problem or a printing error. It was a symptom of something much deeper. Chemistry, at the midpoint of the 19th century, was quietly falling apart from the inside. The crisis had been building for decades. John Dalton had given chemists the idea of atoms in the early 1800s, and the field had run with it enthusiastically, perhaps too enthusiastically, because the concept arrived without a reliable method for actually measuring how heavy one atom was compared to another. Different chemists used different reference points, different experimental techniques, and different theoretical assumptions to arrive at their atomic weights, and the results were a mess. Chlorine's atomic weight was listed as 35.5 by some, 71 by others. Oxygen appeared as 8 in certain systems and 16 in others, depending on whether you took water as HO or H2O as your starting assumption. This wasn't mere disagreement about fine details. The atomic weight of an element was supposed to be a fixed, universal property of nature. If chemists couldn't agree on what it was, they couldn't agree on formulas. If they couldn't agree on formulas, they couldn't reliably compare experimental results across different laboratories or different countries. Chemical equations became nearly untranslatable between research groups. A textbook published in Berlin might be using a completely different numerical language than one published in Paris or London. By the late 1850s, the German chemist August Kekulé had catalogued the confusion explicitly. There were, he noted, at least 3 competing systems of atomic weights in widespread use, producing formulas so incompatible that meaningful scientific communication was becoming genuinely difficult. The problem wasn't that chemists were bad at their jobs. It was that they had no agreed-upon foundation, no shared yardstick. And without that, the science of chemistry, for all its laboratory achievements, could not function as a coherent predictive enterprise. You could describe what you observed, but prediction, the real test of a scientific theory, required consistency you simply didn't have. This is the context that a 2-minute summary of the periodic table always skips, because skipping it lets you get straight to the triumph. But the triumph doesn't make sense without it. What happened next wasn't a lone genius having a vision. It was a field pulling itself back from the edge of incoherence, one careful methodological step at a time. In September of 1860, somewhere between 140 and 150 chemists traveled to Karlsruhe, Germany, for what is now recognized as the First International Chemistry Congress. The event had been organized by Kekulé, Adolf Wurtz, and Karl Weltzian specifically to address the atomic weight crisis, and by most contemporary accounts, it did not go well at first. The debates were circular, the disagreements entrenched. Different schools of thought talked past each other with polite but total mutual incomprehension. It looked, at various points, like the conference would simply dissolve without resolution. Then, on the final day, a young Italian chemist named Stanislao Canizzaro distributed printed copies of a paper he had written 2 years earlier, and something shifted. Canizzaro's argument was not new in its core idea. It was built on work that Amedeo Avogadro had published as far back as 1811, work that had been largely ignored for decades. Avogadro had proposed that equal volumes of different gases, at the same temperature and pressure, contain the same number of molecules. If you accepted that principle, it gave you a consistent way to compare molecular weights from gas density measurements, and from molecular weights, you could work backward to reliable atomic weights without needing to assume anything about formulas in advance. Canizzaro had taken Avogadro's long-neglected hypothesis and developed it into a systematic, practical method. His pamphlet laid it out with unusual clarity. The German chemist Lothar Meyer later described reading Canizzaro's paper on the train home from Karlsruhe. The scales, he wrote, seemed to fall from his eyes. It was the kind of clarity that arrives when a question you've been asking wrong suddenly gets reframed correctly. For many of the chemists at Karlsruhe, the paper had the same effect. Within a few years, the field had largely converged on a single consistent set of atomic weights. Hydrogen was 1. Oxygen was 16. Water was H2O. The foundation had been poured. What you built on it next was the question. What followed, in the early 1860s, was something that happened the way many scientific discoveries happen. Multiple people, working independently, began to notice the same pattern in the freshly standardized data at roughly the same time. This is not a coincidence. When a field suddenly gets access to reliable numbers, the people who are most deeply immersed in those numbers tend to see the structure first, and several people were very deeply immersed. In 1862, a French geologist named Alexandre-Émile Béguier de Chancourtois did something genuinely unusual. He arranged the elements by atomic weight on a cylinder, spiraling upward so that elements with similar properties landed near each other vertically on the helix. He called it the telluric screw. His method actually worked, at least partially. Chemically similar elements did cluster spatially in his arrangement. But de Chancourtois was a geologist publishing in a geology journal. The paper was presented without the diagram that made it comprehensible, and the chemistry community largely didn't notice it. The idea arrived in the world and vanished. John Alexander Reyna Newlands, a British chemist, took a different approach in 1865. He noticed that when elements were arranged in order of atomic weight, every eighth element seemed to share properties with the first, a pattern he compared to the octaves of a musical scale. He called it the law of octaves and presented it to the Chemical Society of London. The reception was contemptuous. One member of the audience, and this account appears in the Chemical Society's own records from the meeting, asked whether Newlands had tried arranging the elements alphabetically to see if that also produced a pattern. The implication being that his method was essentially arbitrary. The Society declined to publish his paper. Newlands's observation was real, but it held only for the lighter elements and broke down further up the scale, which gave his critics a legitimate technical objection alongside their dismissive tone. Lothar Meyer, who had that clarifying moment on the train from Karlsruhe, was constructing his own periodic table through the mid-1860s. His work was rigorous and visually compelling. When he plotted atomic volume against atomic weight for the known elements, the result was a beautifully regular wave, with peaks and troughs corresponding to the chemical families. Meyer's graph made the periodicity undeniable as a visual phenomenon. He completed a full table in 1868. It did not get published until 1870, through a series of delays whose exact causes historians still debate somewhat. That timing matters for reasons that will become clear shortly. Meanwhile, in St. Petersburg, a 35-year-old professor named Dmitry Ivanovich Mendeleev was writing a chemistry textbook. The reason this matters is that textbooks, unlike research papers, require you to organize everything coherently for a student who has no prior knowledge. You cannot wave your hands at gaps in your understanding. You have to make choices, and the choices reveal where the structure is unclear. Mendeleev later described his frustration with the lack of any natural organizing principle for the elements, a frustration that was both pedagogical and scientific. He needed to explain to students why the elements were the way they were, and he didn't have a satisfying answer. On what is recorded as the 1st of March, 1869, in the old calendar then used in Russia, Mendeleev presented a paper to the Russian Chemical Society outlining what he called the dependence of the chemical properties of the elements on their atomic weights. He had arranged the 63 elements then known into a table organized by increasing atomic weight, with elements of similar chemical properties aligned in vertical columns. So far, this was not radically different from what Newlands and Meyer had done. What Mendeleev did next was different. He didn't just arrange the elements that existed. He left gaps. This is the move that distinguishes a list from a theory. When the pattern suggested that an element should exist in a particular position but no known element fit, Mendeleev did not force an ill-fitting element into the slot, and he did not pretend the slot wasn't there. He left it empty and stated explicitly that an undiscovered element would eventually be found to fill it. Then, using the pattern of surrounding elements, he predicted that element's specific properties with quantitative precision. Consider what he predicted for the gap he called EKA aluminum, the element that should sit below aluminum in his table. He predicted an atomic weight of about 68. A density of approximately 5.9 grams per cubic centimeter. A low melting point. An oxide that would form in a ratio of 2 atoms of the element to 3 atoms of oxygen. A metal that would probably be discovered by spectroscopic analysis. These were not vague gestures. They were falsifiable numerical claims about a substance that had never been observed. That is what a scientific prediction looks like when it's functioning properly. He made similar predictions for EKA boron and EKA silicon. The table was published, circulated, and received with a mixture of interest and skepticism. Some chemists found it compelling. Others, reasonably, pointed out that arranging things by weight and finding a pattern did not by itself prove that the pattern was real rather than coincidental. The test would have to be empirical. Either the predicted elements existed with the predicted properties, or they didn't. The first answer came in 1875. Paul-Émile Lecoq de Boisbaudran, a French chemist working with spectroscopy, detected a new element in a zinc ore sample from the Pyrenees. He named it gallium. Its atomic weight was 69.7. It was a metal with a very low melting point. It formed an oxide in the ratio Mendeleev had specified. When Lecoq measured its density, he got approximately 4.7 grams per cubic centimeter. Mendeleev read the published results, compared them to his prediction of 5.9, and wrote to Lecoq saying, essentially, that the measured density must be wrong, because the periodic table required a value closer to 5.9. This is a remarkable moment to sit with. A man was telling the discoverer of an element that the discoverer had mismeasured his own element, on the basis of a theoretical table. Lecoq remeasured. The density was 5.94 grams per cubic centimeter. Mendeleev had been right. Lars Fredrik Nilsson, a Swedish chemist, found EKA boron in 1879 in the mineral euxenite. He named it scandium. Its atomic weight, properties, and oxide chemistry matched Mendeleev's predictions closely enough that Nilsson explicitly acknowledged the confirmation in his published paper. In 1886, Clemens Winkler in Germany isolated EKA silicon from a mineral called argyrodite. He named it germanium. Its atomic weight came in at 72.6, against Mendeleev's prediction of 72. Its density was 5.35, against a prediction of 5.5. Its specific heat, its oxide behavior, its chloride chemistry, prediction after prediction held. 3 independent confirmations, in 3 different countries, by 3 scientists who had not been looking for what they found. The periodic table had crossed from an interesting organizational scheme to something that deserved to be called a law of nature. Then, in 1894, the table ran into its first serious anomaly. Lord Rayleigh, a British physicist, had been puzzling over a small but persistent discrepancy in the density of nitrogen. Nitrogen isolated from chemical compounds was very slightly less dense than nitrogen isolated from air. The difference was around 0.5%, which is the kind of discrepancy that many scientists would attribute to experimental error. Rayleigh didn't dismiss it. He began working with William Ramsay to investigate, and what they found was not a measurement artifact. The nitrogen from air contained a small amount of something else, a gas that was chemically inert, that would not react with anything they threw at it, and that had no obvious place in Mendeleev's table. They named it argon. This was, on its face, a falsification event. The periodic table as Mendeleev had constructed it had no room for a chemically inert gas with an atomic weight of around 40. Worse, as Ramsay continued the work through the late 1890s, argon turned out not to be alone. Helium, whose existence had been inferred from a spectral line in sunlight since 1868 but never isolated on Earth, was found in uranium minerals in 1895. Krypton, neon, and xenon followed by 1898. An entire family of elements, all chemically inert, none of them predicted, had simply not existed in the version of the table that had just enjoyed 3 triumphant confirmations. The way the periodic table handled this is instructive. A weaker framework would have shattered. Instead, it accommodated. Ramsay proposed that the noble gases, as they came to be called, formed a new group, an additional column, positioned between the halogens and the alkali metals. The table stretched to include them without distorting the rest of its structure. Mendeleev himself was initially resistant, not to the existence of the new elements, but to some aspects of where they should be placed, partly because their existence also raised pointed questions about whether the table was as complete as it had appeared. But the essential logic held. The table could be extended because it was built on a real underlying pattern, not just on the 63 elements that had been available when it was constructed. What that underlying pattern actually was remained, for decades, essentially mysterious. Mendeleev had found it empirically. He knew the periodicity was real because the predictions had worked. But why atomic weight should determine chemical behavior, why the pattern should repeat at the intervals it did, why some columns should have 2 elements in the shorter periods and more in the longer ones, none of that had an explanation. It was a map drawn before anyone understood why the territory was shaped the way it was. The first major step toward explanation came not from chemistry but from physics. In 1913, Henry Moseley, a 25-year-old British physicist working in Ernest Rutherford's laboratory in Manchester, used X-ray spectroscopy to measure a property he called atomic number, the number of positive charges in an atom's nucleus, which we now understand as the number of protons. When Moseley reorganized the periodic table by atomic number rather than atomic weight, a small number of persistent problems that had nagged at Mendeleev's arrangement simply disappeared. The most prominent of these was the tellurium-iodine anomaly. Tellurium has an atomic weight of 127.6, iodine has a weight of 126.9, and yet tellurium clearly belongs before iodine in the table based on its chemistry. Arranged by weight, they appear to be in the wrong order. Arranged by atomic number, they fall into their correct positions without difficulty, because tellurium has 52 protons and iodine has 53. Similarly, cobalt and nickel, argon and potassium, each pair had appeared slightly out of sequence by weight but fell perfectly into place by number. Moseley's work made the organizing principle precise and physically grounded rather than empirical and approximate. Moseley was killed at Gallipoli in August 1915, at 27 years old. What further contributions he might have made to physics is one of those questions that cannot be answered. The deeper explanation for why atomic number determines chemical behavior came through the development of quantum mechanics in the 1920s. The work of Bohr, Pauli, Schrödinger, and Heisenberg established that electrons around an atom occupy discrete energy levels organized into shells and subshells, and that the chemical behavior of an element is determined almost entirely by how many electrons are in its outermost shell. When you fill a shell completely, you get a noble gas, inert and stable. When you add one electron to a new shell, you get an alkali metal, reactive and electropositive. The periodicity in the table is the periodicity of electron shell filling. Each row represents a new shell being populated. Each column represents elements with the same number of electrons in their outer shell, which is why they behave similarly. Mendeleev's empirical pattern was, it turned out, a direct readout of quantum mechanical structure, discovered 50 years before quantum mechanics existed. But here is where the story stops being a clean arc of discovery and starts being something more complicated, which is to say it starts being more honest about what science actually looks like. The periodic table, for all the explanatory success of the quantum mechanical interpretation, still contains genuinely unresolved arguments that active researchers are having right now. Hydrogen, for instance, appears at the top of group 1 in most standard tables, alongside the alkali metals, but hydrogen is not an alkali metal. It is a colorless, reactive gas that under normal conditions exists as a diatomic molecule. Some chemists argue it belongs in group 17 with the halogens, because it, like them, needs one more electron to complete a shell. Others argue it should sit alone, above the table entirely, marked as categorically distinct. There is no consensus. The placement is a convention, not a fact. The F block, the two long rows typically detached and shown floating below the main body of the table, presents its own ongoing structural debate. The standard depiction separates lanthanum and actinium from the lanthanide and actinide series in a way that many chemists argue is chemically incoherent. The question of which element actually belongs at the left edge of period 6, lanthanum or lutetium, is a live dispute in the chemical literature. The International Union of Pure and Applied Chemistry has not definitively resolved it. And then there are the super-heavy elements, the ones synthesized in particle accelerators, that exist for fractions of a second before decaying into lighter atoms. Oganesson, element 118, sits in the noble gas column. By the logic of the periodic table, it should be chemically inert, like argon or xenon. Theoretical calculations suggest it may not be. At the relativistic speeds that electrons in a 118-proton atom must travel, corrections to classical quantum mechanics become significant enough to substantially alter the expected electron shell structure. Early theoretical work indicates that Oganesson may not behave like a noble gas at all, that the periodicity that is held from helium through xenon through radon might genuinely break down at the far edge of the table. We do not yet have enough of element 118 to test this directly. It has been synthesized in quantities of individual atoms, observed for milliseconds, and it is gone. Whether the table that Mendeleev built from 63 elements in a St. Petersburg apartment in 1869, extended and deepened and quantum mechanically explained over the century and a half since, continues to hold in the super-heavy regime, remains an open experimental question. The monument is still under construction. The pattern that seemed to reveal itself completely is still, at its edges, dissolving back into uncertainty.